Hello everyone, this is Vasan, a 9-pointer at IIT Bombay from the Department of Civil Engineering. For today's lecture is about normal stress, a part of axial loading. So we already know that load has two consequences. One is internal forces and other is deformations. We already completed internal forces in previous lecture, and to understand deformations we need to know about normal stress and normal strain. Today's topic is about normal stress. So if you consider a member with equal and opposite force P, as this force P is along the longitudinal axis of the member, this is a axial load. So if you cut any cross section, so what is the load at that cross section? This is P from equilibrium. This is also P. So see, this force P here is resisted by the particles in this cross section, right? So that is the reason why equal and opposite force P is created here, right? So but how these are resisting this force? See, there will be bond between the particles, right? So this is one bond, this is one bond, this is one bond. So when you try to apply load P here and load P here, so you are trying to take away this particle towards left, but there is bond between this particle and next particle. So what this particle will do? This particle will apply a opposite force on this particle to stop this, right? So similarly from this side, if you see, this load P is trying to move this particle to right. So what this left particle will do? Left particle will apply load P on this particle to stop this from moving away, right? So see, you might study it in JE. A bond can be treated as a spring with some stiffness K. Okay. So if you see, what is the spring? See, if you apply a force P to a spring, what will it do? It will try to resist, right? So it will create, suppose this is the change in length is x, then spring force will be F is equals to Kx, that will be is equals to P. So it will try to create equal and opposite force P. So similar to that, here also the total force P is resisted by the particles in this cross section. Okay, all particles combinedly resisted total force P, but what about the particles in Chotusa area dA? How much these particles resisted? So then there is a need for the term force per unit area, right? So that is what we call as stress. So but here the stress is normal to the cross section. This normal stress is denoted by sigma. So as this stress is normal to the cross section, it is known as normal stress. So see, so stress at a point can be set as limit delta P by delta A. Delta P is the amount of force resisted by the particles in the area delta A. So delta A tends to 0, right? So then it can be said as dP by dA. So similarly, over the cross section, there will be some sigma, right? It may be equal, it may not be equal, right? So sigma, 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 sigma. But see, if you sigma into dA, if you take a Chotusa element dA and you multiply with stress and you integrate on whole area, whole cross section, then you should give load P, right? So what is the magnitude of the stress? So let us deal about average stress. So what is average stress? Average stress will be defined for a cross section. So in the cross section, what is the total load resisted by the particles? That is P, that is total load. What is the total area? A. This is sigma average for a cross section. See, in a cross section, there is variation in the normal stress, right? But in average sense, the average stress is total load resisted by that cross sectional area divided by total area. That is the average normal stress. See, let us first I should say one thing. If the load is resisted in perpendicular to the cross section, then it will create a normal stress, right? It will create normal stress. This is normal stress. There is one more stress, that is shear stress. Means see, if you apply load parallel to the cross section, then particles will try to resist in this direction, right? So then it will create shear stress. It is denoted by tau. It is denoted by sigma, right? So if this is of area A, then tau average, what it will be? It will be again is equals to P by A. Then what is sigma average? It is equals to P by A. But there will be variation of normal stress in this cross section, right? And similarly, there will be variation of the shear stress in this cross section. So let us understand the distribution of the normal stress over a cross section. So see, there can be two types of loads. One is concentrated external load, another is distributed external load. See, if you see this diagram, here it is concentrated, means it is applied at a point, right? If you apply a load at a point, then see, it is clear. If you take a piece of cloth and mark lines in this checker type, and you apply equal and opposite force point load P, then you will observe non-uniform distribution of stress here. Non-uniform distribution, non-uniform, uniform normal stress distribution, right? So at the place and near the place where point load is acted, there will be variation of the normal stress. So that is the reason there will be non-uniform here. There will be non-uniform deformation, i.e. not similarly non-uniform deformation and non-uniform stress distribution, non-uniform stress distribution. But when you come to the middle region, it will be uniform. It is observed experimentally. But see, at every cross section, if you cut every cross section, the overall load should be P, right? But the sigma normal stress may vary in the cross sectional area, but the overall stress, means integral sigma into dA over the cross section, should be is equals to P, because this is in equilibrium. But if you see distributed external load, means if you take a member and you apply distributed load, uniformly distributed load, then you cut any cross section, the distribution of normal stress will be uniform, right? It is clear. So here sigma average will be is equals to sigma, because entire cross section will have same normal stress. So sigma average will be is equals to sigma, that will be is equals to P by A. Okay. So see, in the case of point external load, at ends there is non-uniform distribution of the normal stress, but in the middle there is uniform distribution, right? So while solving problems, we neglect this non-uniform distribution. We assume that entire member has uniform distribution of normal stress. So to assume that it should fulfill one condition. What is that condition? See, you are assuming that at a cross section the distribution of shear stress is uniform, right? So see, and so where should this net load P should act in this cross section? At what point it should act? Then see, this is the point where the net load P is acting, and over this cross sectional area shear stress is distributed uniformly. So you can say that yes, P1 into y dash is total movement created along x direction. See, this is total movement create. This is the load. This is P. See, P is perpendicular to the cross section, and y. If you see y is this. So what is the direction? It is along x, right? So see, this is y, and this is P. So what will be the direction? Direction will be along x, right? Along x. So this is about x. Movement about x. So movement about x axis. This should be is equals to sigma dA into y integral, right? Integral over the cross section. We said that the distribution is uniform. So sigma outside integral y dA, right? So y dash will be is equals to sigma is P1 by A. So it will be integral y dA by A. What this signify? This is nothing but y centroid, right? So this is y coordinate of the centroid of this cross section. So similarly, if you consider m about y axis, then it will be P1 into x bar, that is equals to integral sigma dA into x, that will be is equal gives rise to x bar is equals to integral x dA divided by A. This is x centroid. So this is x coordinate of the centroid of the cross section. So what does this signify? So for uniform stress distribution, the line of action of force must pass through the centroid of cross section. That is the point. So with this we end for today. In next lecture we are going to discuss about normal strain. Until then, take care. Bye bye from 9pointer.